Hello, and welcome to a lecture on bandwidth and Q. My name is Steve Ellingson. Here's an overview of this lecture. First, a quick rundown of bandwidth concepts. We'll talk about resonance very briefly. You know what this is, but let's put it in context. We'll talk about Q, which we've introduced previously as a useful parameter in impedance matching, and now we'll flesh out that concept a little bit. We'll talk about the Q parameter approach to reel-to-reel impedance matching. Again, we've talked about this in a previous lecture, but we'll now revisit it in the context of these other concepts that we've brought up. And then the path forward. We'll use these insights to design impedance matching circuits that have lesser or greater bandwidth, or at least we'll set the stage so that we can do that. So, bandwidth of impedance matching. When we use reactances, the performance of the match is strongly dependent on frequency. If we pay attention to only one frequency, then we end up with narrowband matching. Now, narrowband matching doesn't necessarily mean that the match has some very limited bandwidth. In fact, the bandwidth could be very large. What makes a match narrowband is the fact that it's perfect or specified only at one frequency and unconstrained to all other frequencies. So it's not really a characterization of the bandwidth of the match, it's more a description of the requirements that we used to develop the match in the first place. Sometimes we need matching with greater bandwidth than what we get from these narrowband methods. And sometimes we desire matching which has narrower bandwidth. There are applications in both senses of this term. Now, this is different from filtering. Here we're trying to achieve an impedance match first and then obtain some bandwidth. Typically in filtering, we're not trying to do an impedance change and we're simply trying to set a bandwidth or a frequency response. We'll come back to filtering in a future lecture. Here, what we're trying to do is establish impedance matches and then, as needed, adjust their bandwidth to meet other requirements we may have. Bandwidth defined. First, note well that there is no fundamental definition of bandwidth. Bandwidth is not a fundamental property of anything. There are only functional definitions of bandwidth. For example, half-power bandwidth is probably the one that you're most familiar with. Half-power bandwidth is a separation between frequencies at which the TPG has degraded by a factor of 2, or that is 3 dB, relative to the nominal, presumably central value. So half-power bandwidth is a concept that you're familiar with, but is certainly not the only way to define bandwidth, and the other definitions give you completely different values. These other definitions include, for example, 1 dB bandwidth. So as opposed to specifying the frequency separation between 3 dB points, you might specify the separation between 1 dB points. Or 10 dB points. I will tell you that both of these alternative definitions are commonly used, not just in RF engineering, but in other disciplines. Yet another way to define bandwidth is 99% bandwidth. 99% bandwidth is a separation between frequencies which contains 99% of the power. Yet another definition is noise equivalent bandwidth. Noise equivalent bandwidth works like this. What you do is you say you have some weird kind of response that might look like this and contains therefore this much power, right? The power under the curve. So the line is power spectral density. The area under the curve is power. And then what you do is you say, look, what happens if I take all that power and I rearrange it like this? Well, then I still have power P. I've just rearranged it so that it has this brick wall response. And the new frequency separation is this. This separation is the noise equivalent bandwidth. That's what we mean by noise equivalent bandwidth. So that's a perfectly reasonable definition as well. So noise equivalent bandwidth, 99% bandwidth, 1, 3, 10 dB bandwidth. These are all definitions that are commonly used and have applications. Yet another approach, and the one we're specifically going to invoke now, is to define bandwidth in terms of energy transfer. So the concept works like this. We begin with a passive two-port. A passive two-port has only passive components, resistors, inductors, capacitors, and so on inside it. In other words, reactive, that is L's or C's, and resistive, that is R's only. And to this thing we apply a sinusoidal source. Now the reason we specify a sinusoidal source is because we want only one frequency. We want to consider one frequency at a time, and that's a sinusoid. And then at the output, we have a passive load, something that can dissipate or absorb power. And one other thing I'm going to specify here for the purpose of this discussion is that we have steady state conditions. In other words, any transient conditions, startup transients, anything that may have been active before we started this experiment, all those transients have died out and we're at the steady state condition. Now at the input, let's consider injected power. Now remember, power is energy per unit time. So I'm interested in the energy per unit time that I'm injecting into this two-port. At the output, the relevant thing to consider is the power transferred out. Now that power might be dissipated in the load, or it may be that this load is transferring the power to yet another place. Doesn't really matter. The passive load is a place where power can be transferred out of the two-port. That's the operative idea. Within the two-port, things that can happen include, well, power can be dissipated. That's something that resistors will do. Or energy can be stored. That's what inductors and capacitors can do. Now, inductors and capacitors cannot dissipate power, at least the ideal inductors and capacitors can't, right? And ideal resistors can't store energy. So in this simplified but completely reasonable thing to consider, these are the things that can happen. We can inject power, energy can be stored, power can be dissipated, or power can be transferred out. Those are all the options. Now, from the principle of conservation of power, we know that injected power equals power transferred out plus power dissipated plus power stored. In other words, all the power that we inject in this direction must go somewhere. And those options are, it can be transferred out, it can be dissipated, or we can be storing energy. Those are the things that can happen to energy that we inject at the input. Now we can also think of this in terms of energy transfer, right? So let's make the following definition. B sub Q. B sub Q is a type of bandwidth I would now like to define. I will define B sub Q in the following way. I will define it as the ratio of these two things. The thing in the numerator is the energy escaped out of the two-port per period of the sinusoid, right? This is a sinusoidal input, so I can define the period of that sinusoid. So the numerator is energy escaped per period of the sinusoid. In the denominator, I have U sub st, which I'm calling the energy stored in one period. So for each period, I have a certain amount of energy which is stored within inductors and capacitors. So this is an unusual definition of bandwidth, probably, if you haven't encountered it before, but it's a completely reasonable way to define bandwidth. I'll show you this in just a moment. Here we go. I've rewritten this definition up here. B sub Q, this new definition of bandwidth, is equal to the energy escaped per cycle divided by the energy stored. Now first, note this is dimensionally correct, right? This is energy, this is time, so this is energy divided by time, and this is energy, so I get units of 1 over time, right? Which is the same as bandwidth. So dimensionally, it's correct. Now just think about this for a second. If I have no reactances, in other words, if I have no L's or C's, then there can be no energy storage because resistors alone can't store energy. So U sub st is equal to 0. The stored energy is 0. And by this definition then, B sub q tends to infinity. That means by this definition of bandwidth, if I have no reactance, then I have infinite bandwidth. But that should make sense to you. Let me give you an example. We've talked about resistive matching, matching that consists only of resistors, and we realized that that has infinite bandwidth. That is exactly this case. So if I don't have any reactances, I have only resistances, and that's what I'm using to make the match, I can have infinite bandwidth, at least in terms of this definition B sub q. And I'll tell you it's true in general as well. Now, if there's no escape of energy, in other words, if there's no energy leaving the two-port into the termination, then there is only storage. All right? In that case, B sub q tends to 0 because U sub es is equal to 0. Now think about that for a second. There is only energy storage, there's no dissipation within the two-port, and there's no escape of energy into the termination. In that case, we would say the two-port is frozen. Now that's an informal term. What it means is just nothing can happen. The capacitors fill up with how much energy they're capable of storing. The inductors fill up with whatever energy they're capable of storing, and we're done. In that case, everything freezes up and the bandwidth is 0. It's 0 in the sense that the signal at the output can't be time varying anymore. It can't be time varying anymore because we've filled up all the reactive devices with energy and they are unwilling to budge at that point. So since the output signal cannot be time varying, the bandwidth must be 0. Again, this should make sense intuitively to you. So we see that in these two extreme cases, where we have no reactances and no escape, we get the expected result for the bandwidth. Now, all other cases, including all practical realizations, are intermediate to these two cases. There's going to be some storage in reactances, there will be some escape, and so we'll have intermediate values of B sub q, that is values between 0 or greater than 0 and less than infinity. And that shouldn't be surprising either. Now note that B sub q itself is frequency dependent. It's frequency dependent because the way we defined it includes t. That is, it knows about the frequency of the sinusoid because t is the period of the sinusoid. So this is a little bit weird. This is a definition of bandwidth which itself depends on frequency. So this is really an expression of what the bandwidth looks like from the perspective of one point on a frequency response curve, right? I can have a magnitude of frequency response that looks like this, and I can define B sub q at one point, and it says something about what the bandwidth is, but only at that point. And if I go to some other point, in principle, I'd get a different value of B sub q. Resonance is the next thing I want to talk about. Resonance is a property of two ports containing only reactance and resistance. So if we have passive things, L's and C's and R's, then we can talk about the resonance of that thing. At resonance, reactances cancel such that there's no additional energy storage. That is, power transfer is limited by loss, that is, by R alone. And if you think about that, that's the way that we have been talking about doing impedance matching, is trying to get TPG equal to 1. So, for example, discrete two-component L-type matches between real impedances, well, those have precisely one resonance, and it occurs at the design frequency, and that is by design. So now we're ready to talk about quality factor. Quality factor is given by the parameter Q. Now we've already invoked a parameter Q in previous lecture, and this will be the same Q, but let's see how that comes about, and let's forget about everything we already know about this parameter Q, and let's just start from a definition. This definition goes like this. Omega naught is 2 pi f naught. That's the usual thing. And B sub q is frequency dependent. So we have to say what frequency we're evaluating B sub q at. in this definition, we're evaluating B sub q at omega naught. In other words, we're evaluating it at this frequency, omega naught. And we're going to say that omega naught is whatever it is at resonance. All right, so the way we're going to define Q is to first identify the frequency of resonance, calculate omega naught, calculate BQ at that frequency, and take the ratio of the two. Now we can invoke the definition of B sub Q to get this new expression. This omega naught here will pull out front, and B sub Q inverse equals the energy stored over the energy escaped. Now that'd be normally divided by T, but here we're going to say times F naught. This sinusoid had a period T. The sinusoid is at the frequency of resonance, so it's T naught, and we'll just go ahead and take care of the reciprocal by substituting F naught. And then further, since omega naught is 2 pi F naught, these F naught appearing in these two expressions will cancel out. So we're left with a 2 pi out front. So we can write it this way. We can say 2 pi times the stored energy divided by the escaped energy, and this is over one cycle at resonance. So another way of talking about Q is that's the ratio of stored energy to escaped energy, right? It's evaluated over one cycle of the sinusoid at the frequency at which the circuit's resonant, and we have this factor of 2 pi out front. Now, quality factor is a way to quantify the steady state energy storage of a two-port relative to the energy escape per period at resonance. That's what this expression is saying. So this is a statement in words of what this expression is trying to say. This metric, Q, or quality factor, is commonly used to quantify the performance of inductors and cavity resonators. You may or may not know this already, but this is where it gets its name. However, this particular use of the term is not what we have in mind now. It's true, but it's not really relevant to what we're working on at the moment. Instead, note that Q is inversely related to this bandwidth, B sub Q, right? We see that here. We see Q here, we see B sub Q here, and as far as we're concerned, omega naught can be a constant of proportionality. So we see that the larger B sub Q is, the smaller Q should be, and vice versa. So now we see that there is a fundamental relationship between Q and B sub Q. One more thing to look at here is I can go back to this expression, which I've rewritten here, and I can observe here that this, again, can be rewritten U sub ES divided by T naught. That's energy per unit time, so that's power. So another way of thinking about Q is that it is the ratio of energy stored to power that escapes times omega naught. That's yet another way of thinking about it.